Think of the old Bertrand Russell skeptical scenario where you say, for all we know, the world might have started only 5 minutes ago in the physical condition that we took it to be in 5 minutes ago, and we would have no way of telling the difference now. If Jacob's theory were true, we would have a way. This is a way of making vivid how novel this proposal is and how different it is from other fundamental physical theories that we've entertained in the past.
This has been a long time coming. We're hot off of the release of my discussion with Jacob and Tim about Jacob's approach to quantum mechanics. And David, I know before we started, you wanted to make sort of some introductory remarks about your perception of the indivisibility approach. So I just wanted to give you the opportunity to start with that.
Sure. Um, um, let me start by saying a little bit about what I'm going to do over the next 30 minutes or so. For 30 years or so now, those of us who've been trying to make old-fashioned, realistic, literal sense of the foundations of quantum mechanics have been struggling mightily with the question of what to make of the quantum mechanical wave function. The trouble, in a nutshell, is that the wave function is a fantastically high-dimensional object, and that the business of admitting such objects into the inventory of the fundamental physical furniture of the universe would seem to require that the fundamental physical space in which the history of the world plays itself out is fantastically high-dimensional as well. And that, in turn, raises a subtle and difficult question about how it is that that high-dimensional space might contrive to appear to us to have only three dimensions that we take, only the three dimensions that we take ourselves to move around in our everyday experience of the world. And what I'm going to be talking about here is a new picture of quantum mechanics, a picture that proposes to simply do away with wave functions, which is originally due to Jacob Barandes, who's here with us today, too. And I'm going to approach that picture here as an attempt at understanding quantum mechanics as an exact and complete and literal and realistic account of the microscopic inner workings of the universe as a whole. And I should note, and we'll see if this is out of date by now or not, because Jacob has told me about some recent developments. I should note that that Jacob himself, if I understand him correctly, is suspicious for a variety of reasons about the very idea of an exact or literal or complete scientific description of the universe as a whole. And these suspicions seem to play an important role, at least in the discussions I've had with Jacob some months ago. They seem to play an important role in shaping what Jacob is inclined to expect and in limiting what Jacob is inclined to demand of a satisfactory proposal for a fundamental physical theory. I'm not going to discuss those suspicions here. That would take us much too far afield, except to record that I don't share those suspicions myself. But I want to be clear at the outset that I'm going to treat Jacob's picture of quantum mechanics here for whatever it may turn out to be worth, and however he himself may have intended it, as an attempt at making straightforward, old-fashioned, flat-footed metaphysical sense of quantum mechanics in the manner of, say, Bohmian mechanics, or of the GRW theory, or of the many worlds interpretation of quantum mechanics. And in particular, I'm going to be holding it to the same standards of clarity and exactness and universality as I'm accustomed to demanding of those other proposals. That is, at least insofar as I understand the words, I'm going to be taking it seriously. And I'm gonna want to argue, moreover, that it ought to be taken seriously and that it rewards being taken seriously. So, whenever I refer in what follows to Jacob's picture or Jacob's version or Jacob's theory or Jacob's proposal, the listener should bear in mind that what I'm referring to is this exact and complete and universal way of reading the theory. Whether that happens to correspond to Jacob's own way of reading it or not. One more thing about my presentation here. I'm unfortunately going to need to take it for granted that the listener or the viewer is familiar with the standard quantum mechanical formalism and with the standard strategies for solving the measurement problem, Bohm's theory, or the GRW theory, or the many worlds interpretation of quantum mechanics to which that standard formalism gives rise. Otherwise, the presentation would just need to go on for hours and hours rather than the 30 or at most 45 minutes that I've been allotted for this introductory spiel here. Um, but there are many places now to find very accessible accounts of that formalism and of those strategies. And indeed, many of the previous installments of Robinson's podcast, including some that I myself have participated in, include very accessible accounts of that formalism and those strategies. Okay, with those disclaimers out of the way, let me start by laying out what I'll be referring to in these remarks as Jacob's theory. So, I'm going to present Jacob's version of quantum mechanics in a way that's not exactly his way of presenting it, but which amounts nonetheless to a way of presenting exactly his theory. If again you read his theory as an attempt at understanding quantum mechanics, as an exact and complete and literal and realistic account of the microscopic inner workings of the universe as a whole. It has, in particular, exactly the same fundamental ontology as Jacob's theory does, and it makes exactly the same claims about how those fundamental ontological constituents of the world behave as Jacob's theory does. I'm going to present it in my way rather than in Jacob's way, because I find my way easier to follow and easier to reason with and easier to connect and compare with the standard quantum mechanical formalism. The fundamental ontology of Jacob's version of quantum mechanics, at least in the non-relativistic first quantized case, consists entirely and exclusively of some presumably finite collection of particles. Just as in the case of classical mechanics, each of those particles invariably has some perfectly determinate position in space, and the history of those positions, the history that is of the configuration of that collection of particles, constitutes the complete history of the physical world. And what Jacob's theory gives us is a way of assigning a definite numerical probability to every possible such configuration at any time t, given the configuration at an initial time t0. The procedure for calculating those probabilities is as follows. Stipulate to begin with that the quantum mechanical wave function of the world at t0 is that eigenfunction of the configuration operator whose eigenvalue is the one associated with the actual configuration of the particles at t0. And let me pause here to acknowledge two fairly urgent questions, which will likely already have arisen in the listener's mind. One of Jacob's central claims for this theory is precisely that it does away with wave functions. And notwithstanding the fact that I've just now alluded to something that I called the wave function of the world, I think there's a very important sense in which Jacob's claim is correct. Bear with me. Everything will be clear. Everything will be explained in a minute. Second point, less important point, there are, as everybody knows, no such mathematical objects as eigenfunctions of location or configuration in ordinary continuous position space. Those are just not well-defined, internally consistent mathematical objects. put that worry aside for the moment, pretend just for the time being, and just in order to keep the initial sections of this discussion as simple and as accessible as I can, that there are such mathematical objects as eigenfunctions of particle configuration, and that those eigenfunctions can, moreover, be plugged into the Schrodinger equation as initial conditions. I'll return to this worry, and Jacob may have new things to say about this particular worry later on. So I'll return to it briefly, and I'm sure Jacob will have something to say about it. Good. With that on the table, let's start again. The procedure for calculating the probability of any particular configuration of the world at any time t greater than t0, given that the configuration of the world at the initial time t0 was some configuration c, is as follows. Stipulate that the quantum mechanical wave function of the world at t0 is that eigenfunction of the configuration whose eigenvalue is the one associated with the configuration C. Then evolve that initial wave function from t0 to t in accord with the Schrodinger equation. Then evaluate the probability of any particular configuration C prime at t using the evolved wave function of the world at t and the Born rule, exactly as in standard quantum mechanics. And that's it. That's the whole theory. The rest of what I'm going to have to say here is commentary on this theory, but the theory has already been, at least insofar as I understand it, um, put explicitly and exactly on the table. Good. Here's the commentary. Section 1, the role of the wave function. Let me begin, as promised, with the question of the metaphysical status of the wave function in Jacob's theory. Think by way of comparison of Bohmian mechanics or of the GRW theory. In Bohmian mechanics, a dynamically complete specification of the initial conditions of the world involves a specification of both the initial particulate configuration of the world and of the world's initial wave function. And note that although the choice of the initial wave function of the world probabilistically constrains the choice of the initial particulate configuration of the world, the choice of an initial particulate configuration of the world in no way constrains the choice of the initial wave function of the world. In Bohmian mechanics, in other words, the wave function of the world enters into the specification of the initial physical conditions of the world as a separate and independent and freestanding fundamental degree of freedom. And nothing like that is the case on Jacob's theory. The business of specifying dynamically complete initial conditions of the world on Jacob's theory is entirely and exclusively a matter of specifying the initial configuration of the world. And it is that initial configuration all by itself that determines what initial wave function we're going to need to plug in to the Schrodinger equation in order to calculate the configuration probabilities later on. You might say that on Jacob's theory, the role of the initial wave function of the world is merely to represent, in a particular mathematical language, the initial particulate configuration of the world. And the contrast between the role of the wave function in Jacob's theory and the role of the wave function in something like the GRW theory is even more stark. In Bohm's theories, I've just said, the wave function of the world enters into the specification of the initial physical conditions of the world as a separate and independent and freestanding fundamental degree of freedom. In the GRW theory, on the other hand, a specification of the initial wave function of the world is literally all there is to a specification of the complete dynamical conditions of the world. And mind you, this is true whether we're working in an interpretation of the GRW theory on which the wave function of the world is the unique, fundamental, concrete physical object, or in interpretations that add what people call a primitive ontology in the form of, say, mass densities or flashes, because the primitive ontological history of the world, if there is one, is uniquely and entirely determined on these interpretations by the history of its wave function. and not the other way around. And again, nothing like that is the case on Jacob's theory. And so, on Jacob's theory, unlike in Bohmian mechanics and unlike in the GRW theory, there is simply nothing at all, insofar as the metaphysical status of the wave function is concerned, to wonder about or to worry about or to debate about. The wave function, on my way of presenting Jacob's theory, is an entirely innocent and unmysterious mathematical instrument, an element of one particularly simple and straightforward way of formulating the law that gives us the probability that the world has this or that particular configuration at any time t as a function of its configuration at the initial time t0. And the law in question here can be formulated in other ways, as Jacob himself does, which make no mention of wave functions. And it is that law, however it may happen to be formulated, that I take it exhausts the physical content of Jacob's theory. And so the fact that wave functions get alluded to in my way of presenting Jacob's theory shouldn't be construed as an indication that what I'm presenting is anything other than Jacob's theory itself. And the fact that wave functions get alluded to in my way of presenting Jacob's theory should not be construed as in any way undermining Jacob's claim that wave functions are no part of the fundamental physical furniture, of the world that his theory describes. Jacob's theory, if it can be made to work, and if it can be made sufficiently plausible and adaptable and attractive, might simply do away at a single stroke with all of the questions that have been troubling us for 30 years now, as I mentioned, about what wave functions are. And this strikes me as a noteworthy and exciting possibility, and one that I think merits careful study. Good. Second section of commentary, indivisibility. Consider the structure of the various proposals for a fundamental physical theory with which we've become familiar since the scientific revolution of the 17th century. The laws of Newtonian mechanics determine the complete physical condition of the world at any time, given the complete physical condition of the world at any other time. And exactly the same thing is true of Maxwellian electrodynamics, and exactly the same thing is true of, say, Bohmian mechanics. The case of the GRW theory is a little bit different. The laws of the GRW theory determine a unique probability distribution over the possible complete physical conditions of the world, given the complete physical condition of the world at any earlier time. But they tell us almost nothing at all about the complete physical condition of the world, given the complete physical condition of the world at any later time. Good. But these are all minor variations compared to what we're going to get with Jacob's theory. Jacob's theory is not like any of these cases above, and indeed, it's not like anything that we've encountered in fundamental physics before. The laws of Jacob's theory determine a unique probability distribution over the possible complete physical conditions of the world at any given time, given the complete physical condition of the world at a single and specific and particular earlier time. Call it the initial time. And this, because it's so unfamiliar, will be worth rubbing in a little bit. Consider 4 times in the history of the universe: T0, the initial time, and 3 arbitrary later times, T1 and T2 and T3, where T1 is less than T2 and T2 is less than T3. On Jacob's theory, the particulate configuration of the world at time T0 will determine unique probability distributions over the possible particulate configurations of the world, as I said above, at T1 and T2 and T3. But the particulate configuration of the world at T1, which is to say the complete physical condition of the world at T1, is going to tell us nothing over and above what can be inferred from the configuration of the world at T0 about the particular configuration of the world at T2 or T3. And the particulate configuration of the world at T2 is going to tell us nothing over and above what can be inferred from the particulate configuration of the world at T0 about the particulate configuration of the world at T3 or T1, and so on. We are not free on Jacob's theory, as we are in classical mechanics and in Maxwellian electrodynamics and in Bohmian mechanics and in the GRW theory and in standard textbook formulations of quantum mechanics. We're not free, as we are in all those theories, to start with the complete physical condition of the world at any time we like and to calculate from there into the future. And we're not free in Jacob's theory, as we are in classical mechanics and all the other theories I mentioned, to divide up the calculation from T0 to T2 into two separate steps, the first of which takes us from T0 to T1, and the second of which takes us, by the same set of general dynamical laws, from T1 to T2. All of this can be made particularly vivid in the context of the most familiar and iconic experiment in quantum mechanics, the double slit experiment. The situation in the nutshell, as people will remember, is this. You have a source of particles, a screen with two slits in it, and a fluorescent screen on the other side of the screen with the slits in it, where the particle finally lands after passing through the slitted screen in the middle. And our experience in the laboratory is that if we set up a situation like that and release particles from the source one at a time, the probability distribution over possible landing sites on the fluorescent screen is going to display the iconic quantum mechanical interference pattern. And that interference pattern is exactly what you get if you do the calculation in Jacob's theory in a single step, running from the release of the particle from its point-like source at T0 to its landing on the fluorescent screen at T2. But if you break the calculation up into two steps, the first of which carries you from the release of the particle from the source at T0 to just after the passage of the particle through the slitted screen at T1, and the second step carries you from just after the passage of the particle through the slitted screen at T1 to the arrival of the particle at the fluorescent screen at T2, then the probabilities of the particle landing on the fluorescent screen at various different points come out wrong. If you break the calculation up into two steps on Jacob's theory, the interference pattern vanishes. And it is therefore a fundamental tenet of Jacob's theory. It is therefore a fundamental law of Jacob's theory that the two-step calculation is forbidden. The history of the world is, in Jacob's terminology, indivisible. The initial time, which is presumably to be understood in the most general case as the beginning of the universe or something like that, has a special and unique metaphysical status of a kind that has no parallel, insofar as I know, in the previous history of physics. The theory, in what might be more familiar language, is radically non-Markovian. And maybe let me just inject one more word about this to make it clear how strikingly different this is. Think of the old Bertrand Russell skeptical scenario, where you say, for all we know, the world might have started only 5 minutes ago in the physical condition that we took it to be in 5 minutes ago, and we would have no way of telling the difference now. If Jacob's theory were true, we would have a way of telling the difference now. It makes different predictions if you start from the state that we took it to be in 5 minutes ago than it does if you start from the state that we took it to be in 10 minutes ago. Okay, so here's an example of a skeptical hypothesis that everybody assumed would work for physics in general. Okay, this is a way of making vivid how novel this proposal is and how different it is from other fundamental physical theories that we've entertained in the past. This is what we get in a genuinely fundamentally non-Markovian theory. Good. Section 3 of my commentary, the effects of measurements. Suppose we add another physical system to the two-slit case that we've just been talking about, a system that's designed to measure which one of the two slits the original particle went through on its way from the source to the fluorescent screen. In that case, of course, our experience in the laboratory is that the interference pattern at the fluorescent screen disappears. And if we calculate the predictions that Jacob's theory makes about a modified experiment like this, by starting at the moment t0 when the original particle is released from its point-like source and moving in a single step to the moment t2 when the particle lands on the fluorescent screen, we'll find that Jacob's theory correctly predicts that the interference pattern, the pattern of the measuring that the interference pattern in the presence of the measuring device almost entirely disappears. And so, if the position of the original particle is measured at T1 as it's passing through the slitted screen, the result of the one-step calculation of the probability distribution over the possible positions of the original particle at T2 and the result of the two-step calculation of the probability distribution over the possible positions of the original particle at T2 are going to be very nearly the same. And note that if we look at the probability distribution over possible configurations of this more complicated universe at T2, or indeed, if we look at the probability distribution over possible configurations of this more complicated universe at any time later than T2, so long as the pointer on the measuring device is still pointing at the time in question to either the particle went through slit A or the particle went through slit B, and if we conditionalize that distribution on the proposition that the pointer is pointing at, say, the particle went through slit B, then the resulting probability distribution after that conditionalization over the possible positions of the original particle is going to be very close to the one that would have obtained at the time in question if the probability distribution at T1 had been non-zero only in the vicinity of slit B. You might say that this is the statistical vestige in Jacob's theory of the phenomenon of the, quote, effective collapse of the wave function in Bohmian mechanics. Or you might say that this is the statistical vestige in Jacob's theory of the phenomenon of measurement-induced branching in Everett's understanding of quantum mechanics. And this will, of course, be as general a phenomenon in Jacob's theory um, um, as the phenomenon of effective collapses and measurement-induced branchings are in the Bohmian and Everettian versions of quantum mechanics. But note as well, and this is an absolutely crucial point, that none of what we've been talking about over the past few minutes amounts to anything like an exception to the general phenomenon of indivisibility that I discussed in the previous section. And this may be a point on which Jacob and I are going to disagree later on. Jacob has a way of talking about what he calls separation events and so on and so forth, induced by such measurements or by environmental decoherence, something like that. So let's bear that in mind. But yes, it's going to be a premise of how I'm going on from here that this constitutes absolutely nothing like an exception to this generalized indivisibility. Consider again the experiment with the measuring device. Jacob's theory, as we're reading it here, is committed to the claim that the correct way to calculate the probabilities at T2 is to proceed from T0 to T2 in a single step, and that the outcome of the two-step calculation from T0 to T2 is invariably and unavoidably wrong. The two-step calculation is always going to be at least slightly wrong about the position probabilities for the original particle because measuring devices are never entirely perfect. And the two-step calculation is sometimes going to be wildly wrong about the configuration probabilities for the complete universe, including the measuring device, at times at or after T2, because the quantum mechanical interference effects between different branches of the universal wave function can never be made to go away. They can just be put in, larger and larger features of the entanglement of the world. The indivisibility of the complete history of the world on the theory we're thinking about here is, at least as I'm reading it, absolute and inviolable. The sorts of entanglements that are produced by measuring processes can, of course, make that indivisibility, considered as a purely practical matter, less obtrusive and less obvious and less easy to observe, but nothing can make it go away. Good. Section 4 of my commentary. I won't spend much time on this, and I bet Jacob has a lot of news about this, and we can talk about it later. This is the issue of the delta functions of the the eigenstates of configuration. Of course, we can't be using eigenstates of configuration because there are no such mathematical objects, but I suspect that there are various ways to soften that up by analogy with what's done in the GRW theory, for example, where we don't have collapses to eigenstates of position. We have collapses to something like Gaussians centered on a certain position that are relatively narrow, so on and so forth. So I don't want to detain us there, and I suspect that Jacob will have much more to say about that later on. Let me skip to section 5, which I guess is, I think, the important one and the one that'll be worth talking about a lot here. So section 5 of my commentary, which is called the incompleteness of Jacob's theory. What we expect of a fundamental physical theory, I take it, is that it tell us what fundamental stuff there is, and that it tell us what that fundamental stuff does. Jacob's theory does the former, but it only does a part of the latter. It gives us, in particular, probabilities that the configuration of the world will be this or that at any time t, given its configuration at the initial time, t0. But unlike, for example, Bohmian mechanics, it tells us nothing about what path the world may have taken through the space of possible configurations to get there. Here's another way to put it. Jacob's theory, as it stands, gives us probabilities that the configuration of the world is this or that at any time t, given its configuration at the initial time, t0. But for any two times TA and TB, neither of which is the unique and metaphysically privileged initial time T0, Jacob's theory is going to tell us nothing whatever about how the configuration of the world at TB depends on the configuration of the world at TA. One might think that this is not a particularly egregious or particularly worrisome omission. One might think, for example, that the probability that the world has this or that configuration at this or that time must already include everything there is to say about the probability that this or that experiment has had this or that outcome, since those outcomes must presumably supervene on those configurations. And it might be argued that any theory that gets those probabilities right must be empirically adequate. And it might be argued that insofar as Jacob's theory does get those probabilities right, it has already delivered everything that we have any legitimate right to expect of a fundamental physical theory, and that the business of telling ourselves stories about what path the world might have taken from one of those times to another, once those probabilities are already in place, is idle, speculative, unconfirmable fluff. But this is much too fast. Consider, for example, the following way, you might call it the minimal way, of completing Jacob's theory. Here is the minimal completion. 1. The probability that the configuration of the world at any time t is this or that, given its configuration at t0, is the one we get from my original version of Jacob's theory. 2. Second postulate of this minimal completion. Given any two times, ta and tb, neither of which is t0, the probability distribution over possible configuration on this minimal completion of Jacob's theory, the configuration of the world jumps discontinuously around from instant to instant, and the only constraint on the way it jumps around is that at each new instant, the probability that the world has some given new configuration is the one prescribed by my original version of Jacob's original theory. The configuration of the world at any one instant, so long as it is at any instant other than the initial instant, exerts no influence whatsoever over its configuration at any other instant. The configuration of the world at any one instant contains no record or trace or memory of its configuration at any other instant. The traces and records and memories of the past that seem to present themselves at any single instant, although they are all consistent with one another, are all completely unreliable as indicators of actual past configurations. Let me make this a little bit more explicit. Let P sub C star as a function of C and T represent the probability, according to the minimal completion of Jacob's theory that I've been talking about, that the configuration of the world is C at time T, given that it was C star at the initial time T0. And conditionalize P C star as a function of C and T on the existence at time TB of a certain book in a certain existent library in a certain existent city that describes, say, the life of Napoleon. That conditionalized distribution will assign a high probability to the existence at TK of other books and of paintings and of videos and of memories and so on that describe the life of Napoleon as well. And this is an example of the phenomenon that I referred to earlier on as the statistical vestige in Jacob's theory of the Bohmian mechanical phenomenon of effective collapse, or of the Everettian phenomenon of branching. That is, at each moment, the world will contain a whole bunch of what appear to be records of earlier situations of the world, which the linearity of the quantum mechanical equations of motion are going to guarantee are all consistent with one another. But note that this same distribution, the distribution that we attain, that is, by conditionalizing P sub C star as a function of C and T on the existence at time TB of a certain book in a certain existent library in a certain existent city that describes the life of Napoleon, the existence of all these things is going to assign an astronomically low probability to the very existence of the Earth in 1804, or for that matter, 10 minutes ago, or for that matter, at the present minus 1 nanosecond. Okay, it's going to be extremely unlikely, given all these books, not only that Napoleon existed, but that the Earth even existed a second ago. And consider whether there are really any measurements or observers or experiences at all in a world like that. Isn't it absolutely of the essence of what it is to be an observer or a measuring instrument, after all, that the system in question, that is the observer or measuring instrument, responds in certain more or less reliable ways to certain features of its environment? Isn't it absolutely of the essence of what it is to be an observer or a measuring instrument to put it slightly differently, that the system in question, that is the observer or the measuring instrument, is possessed of certain more or less reliable behavioral dispositions. And the problem is that there are no such dispositions, none at all, in this minimal completion of Jacob's theory. And there will presumably be similar worries about the existence of observers or experiences or measuring instruments in other imaginable completions of Jacob's theory, on which the variations in the configuration of the world from moment to moment are not completely random, but nevertheless, whatever this means exactly, too wild. And perhaps it's worth repeating at this juncture that the fact that the positions of macroscopic material bodies are being measured millions of times per second by their environments is completely irrelevant to the considerations of the last few minutes. Those measurement events are going to give rise to probability distributions over possible configurations of the world, which display all of the instantaneous statistical vestiges of Bohmian effective collapses or Everettian branches that I was talking about before. But the facts about which branch of the world, but the facts about which branch the world is apparently on, or about which outcome apparently emerged in some past experiment, or about which quasi-classical macroscopic trajectory the world is apparently following, are going to jump around with no pattern and no continuity and no rules and no limits at each new instant. And so the incompleteness of Jacob's theory, as it currently stands, is in fact, it seems to me, a very egregious omission and a very serious worry. It seems to me that in the absence of any particular suggestion for completing the theory with a law governing these trajectories through configuration space, the question of its empirical adequacy and the deeper and prior question of whether it has any empirical content at all remains at best radically unsettled. Good. I'm going to make this shorter now. Um, I have an additional section on some very preliminary suggestions for completing Jacob's theory with the dynamics. This may be only a testament to my own lack of imagination, but the suggestions that I was able to come up with, although they'll be in some strict sense empirically adequate, are really ugly and grotesque and suggestions that nobody in their right mind would take seriously as a fundamental physical theory. But we'll have to see how that develops. So that's this next section. Let me just say one more thing, and we can get into discussions about this too. I don't have much to say about this. Um, Jacob has has frequently made claims of locality on behalf of his picture. And I guess there are two things I want to say about it. One is, Jacob, and I think Jacob probably agrees with this, Jacob should have been much clearer at the outset about what he meant by locality, because what an average listener who's familiar with discussions in foundations of quantum mechanics would have thought about the claim that he's got a way around quantum mechanical non-locality might have been that he's got a way around Bell's theorem. And that's not what he has. What's going on here is that Jacob is working with a different notion of what it means to be a fundamental physical theory to be local than Bell was working with. This implies that Jacob thinks that the notion of locality that Bell settled on isn't really the good one or the ideal one or the important one to think about. Um, um, I don't have too many opinions about that because I haven't studied very closely what Jacob's competing notion of non-locality is. Let me just say this for people who are familiar with, say, Bohm's theory. Jacob says that on his notion of locality, the question, or at least he has said to me in the past, that on his notion of locality, the question of whether or not Bohm's theory is non-local can't unambiguously be settled. Um, that seems on the face of it like really, really bad news for whatever Jacob's notion of locality might turn out to be, because on anything that seems related to our ordinary English notion of what locality or not non-locality might amount to, it's really, really vivid, as all students of Bohm's theory know, that Bohm's theory wildly violates our intuitions about things only affecting other things directly that are immediately spatially and temporally adjacent to them. But there may be much more to discuss on that score. And I think, let me just sum up. Uh, I'm sorry to have taken, maybe I didn't take that much longer than I said I would. Um, um, Let me sum it up this way. I think this is an interesting proposal. I think it should be very welcome that somebody is putting on the table a way of getting rid of all of the mishigas that investigators of the foundations of quantum mechanics have put themselves through over the past 30 years or so, trying to figure out what to do with the wave function as a fundamental feature of the furniture of the universe. If there's a way of getting rid of that, I think that's exciting. That having been said, um, at least insofar as I've investigated it so far, I think the theory faces daunting challenges. Um, and I'll be interested to see how and whether those challenges get worked out. That's all I have to say.
Excellent. That was absolutely amazing. One thing you did that's very helpful for me, David, is you gave a roadmap for this discussion going forward, and we can kind of break it up into chunks because time is limited, and we can make sure that we touch on a lot of the big points. First, I think before getting into, Jacob, whether you agree with David's formulation of the theory, I think the first thing to touch on is whether or what your thoughts are on realism and whether David is right to treat your account as making straightforward, realistic claims about the world. And
I'd like to start, first of all, by thanking you, Robinson, for organizing this discussion. And of course, immense thanks to David for engaging so much with my work and providing so much incredibly detailed and helpful input and feedback. David, I have benefited immensely from all this feedback, and there have been some developments to share. So I think this is going to be a very substantive discussion. And I think by the end, if you're not fully convinced that this is the right way to go, I think you'll maybe acknowledge that there's been some real productive work in directions that I think you'll find very amenable. So my view of realism, I think, is quite compatible with David's view. Maybe it would be helpful for me to explain how I would describe what's going on in this theory. And then I'll touch on what I mean by realism as I explain it. There's more structure to it than the version that David was describing. The version of the theory that David was describing has a lot in common with a proposal by John Bell in a paper in 1981 called Quantum Mechanics for Cosmologists. Bell was grappling with Everett's theory, the many worlds theory. And he was a little uncertain about exactly what the many worlds theory was trying to say and how it dealt with probabilities. So he described what he called the Everett question mark theory, which Everettians would not say describes their theory properly. But the Everett question mark theory is basically, many worlds, imagine, all the different branches, everything happens. But on this view, only one of the branches is somehow really happening. And which branch is happening more or less randomly fluctuates from moment to moment, but in line with the Born rule, the probability distribution at any given moment specified by the Born rule. So there's no connection between what's going on at one time and what's going on at another time. At one time, there can be a world filled with books about Napoleon and artwork about Napoleon and Earth and all of that stuff. And I love the reference. If I recall, this is from, I think, chapter 4 of Time and Chance, the Napoleon story, which is really great. And then at another moment, the world could be completely different, drawn again from the Born rule probability distribution, some other branch of the wave function. And then in the next moment, some other branch. And although at any given moment, there's sort of a consistent picture of the world, there's no consistency from moment to moment. So this is the Everett question mark theory. And this is very much like the picture of my theory that David has expressed.
Can
So
I
I should say,
jump in, just for, if it's okay, just to make sure we're
of
understanding
course,
each
of
other?
course.
Um, that isn't, of course, the way I was understanding your theory. I was understanding your theory as something without. This is a theory with the dynamics.
Sure.
It's a
Yes.
jumping. I was understanding your theory as having no dynamics at all, and this was a way of making it vivid how limited the constraints imposed by your theory on a dynamics that one might add would be.
Right. So to be fair, the way you described the theory was that it simply lacked dynamical structure, and you gave it a particular dynamical structure just to show the lack of structure could admit
Yeah, that's
something
right.
like the Everett question mark theory.
That's right.
That's
That's the
a
right way
much
to put it.
sharper way to characterize what's
Yeah.
going on here, and that's a reasonable thing to say. So let me describe to you how I would explicate the foundations of this theory, this indivisible theory, and some of this was sort of always implicit. It was sort of how I had been thinking about how the theory worked. But, when you come up with an idea, sometimes you need to talk to people because you need people to push you to make some of your implicit understandings explicit. So some of this was from talking with people, and some of it was also from people who've, made the theory more rigorous. So the theory helps itself to a mathematical theory, the theory of stochastic processes. And the theory of stochastic processes is not, I think, a part of the standard curriculum for folks working in many areas of philosophy, even philosophy of physics with some exceptions. And even many physicists, I think, don't spend a lot of time with the comprehensive theory of stochastic processes beyond simple examples. So some of this work that's helped me understand what I've been trying to say has come from people who come from the mathematical theory of stochastic processes. And so this has really helped me sharpen the kinds of things that I want to say. I should add that this has not only been about people helping me reveal what I already knew by any stretch. I've also, had new ideas, or people have contributed new ideas to this program. So it's been a mixture of all of these things. Now, with that said, let me explain how I would describe the theory now. So to begin, for every system we would like to describe, every physical system in the world in some sense, whether we would call it an open system or closed system, doesn't matter. There is some menu of possible configurations the system could have, and configurations meaning some kind of way that the system is in some ontological or physical sense at a given moment, let's say, in something like physical space or whatever happens to physical space in our modern, physical theories. So if you want to think of a simple model, and David considers a simple model of a non-relativistic system consisting of a fixed number of finitely many particles, the configurations would just be the different arrangements, the different snapshot arrangements of the particles. Those are the different configurations. If you wanted to model a system of fields, the configurations would be patterns of field intensities and directions and polarizations in space. If you wanted to model a discrete register of switches inside of a computer, they would be each configuration would be a snapshot of different configurations. So the ontology is as straightforward as I can make it. It's basically classical like ontology, right? And by realism, I'm saying that we're describing a world in which physical systems have configurations in a somewhat flat-footed sense. akin to how we might think of configurations in classical physics. Now, this isn't because I have some absolute, unwavering commitment to classical type ontology. It may be that in some future physical theory, we really have to abandon this. I see this as an intellectual, a form of intellectual exploration. Can we make such a flat-footed ontology work and still get an empirically adequate theory? The answer may be no, but I think there's still this question: can we make that work? And if we can, well, that would be an interesting thing to do. So that's the first part of the theory, and that's my realism, right? There's
Oh,
every
can
system
I
involved.
just
Yeah,
can I get a clarification about
sure,
that,
please.
Jacob?
Yes.
Um, I just want to press you a little harder on the question of realism. Um, um, I would have thought, and and this isn't just an academic remark. I guess this is the kind of theory I'm looking for when I say I'm looking for a realistic theory. Um, I would have thought that it's part and parcel of realism that one takes there to be an objective, determinate fact of the matter at all times and under all circumstances about the situation of the entirety of existence, of the entirety of the universe. Okay. That's something that I always took to be part and parcel of what it is to have a realistic attitude towards the world. Of course, that leaves all sorts of epistemic questions unanswered. How much can we know about that? Blah, blah, blah. But part of what I mean by a realistic theory is a theory that tells us what physical situations the entirety of existence could or could not be in, and how those situations evolve with time. Is that your picture of realism, or is there someplace you would get off that train?
Well, David, here's just a problem we have with standard quantum mechanics. It's not clear we have a place to stand if you're trying to approach a system that's right in front of you. Every system we have any contact with that we know about is an open system, and open systems are very difficult to work with in quantum mechanics. It's very difficult to give them dynamical rules. So we do this move where we just look to the nearest enclosing closed system, and then we apply the dynamical axioms of quantum mechanics, whether that's the orthodox Dirac von Neumann axioms or something like the Bohm theory or Everett or whatever. And then we apply some rule to how that closed system evolves. And then we look down into the innards, the smaller subsystems, the little Russian dolls inside of our bigger system
Jacob,
to
is
then
is
figure out
that
how they behave.
different from what we do in, say, Newtonian mechanics?
Yes. Yes, it's different.
Say something about that.
Yeah. Yeah. So, yeah. So Newtonian mechanics, if you hand me an object in front of me, okay, so just a body in space or on a table or whatever. In general, that's not going to be a closed system. It'll be an open system. And I can believe on the Newtonian world picture that there is some fact of the matter about the position of the body, its constituent particles. There's some fact of the matter about the velocities of the body and its constituent particles, modulo all the usual concerns about what do we mean by a velocity? Is that really an instantaneous property? Let's put that aside. And I could also believe there's a fact of the matter about what the forces are on that body. Now, I may not know all this information. I may not have full epistemic access for practical or principled reasons. It may be that I simply don't know everything that could be acting on this body. But I can believe if the Newtonian picture were true, I can believe there is a fact of the matter about the position, the velocity, and what all the forces are. And that means that on the Newtonian theory, I can believe there's a fact of the matter about what the next infinitesimal, next moment configuration of this body will be. And then I can believe at that moment that there's some new set of forces maybe on the body. It's got some new position, some new velocity. And so I can believe again that there's some fact of the matter about what its next position will be, and so on and so on.
But
Now,
Jacob, that seems uh, uh, a little bit misleading. The forces, first of all, at the initial moment, and even more so at the next moment, may well depend on the state of everything that there is. So it's still appealing to some notion of the totality of what there is.
Well, that may be the case, but let me come back to this mere logical question. This is important. So, okay, of course, one view could be that there are background forces, then forces that don't come from particles. I mean, one can take a
Yeah,
view of
maybe they
Newtonian
are forces
mechanics
that
that
come from, but we need to know about all the particles that there are.
that's true. That's true.
Yeah.
But my point is, if there's an object in front of you, it is an open system. And whether or not you want to talk about what's going on in the rest of the universe, there's a fact of the matter what those forces are. And I have a law in that tells me, well, my law I can necessarily use because I don't know all the details, but in principle, there's some law that dictates what it will then do. Now, in practice, I don't know all of the forces. I don't know everything exactly. So I make approximations. I come up with an idealized model of this Newtonian system with fewer, simpler forces, with some truncation on the decimal places of the initial position and velocity and so forth. And then I use this model to predict what it's going to do. And I'm aware, even before I've done an experiment, that there's going to be some error bars around my predictions. That is, there's the actual system as represented according to Newton's laws of nature. And then there's my model. They're both phrased within commensurate theoretical frameworks. They're both in Newtonian mechanics. And I can talk about how much deviation there is between them. For example, I could put an estimate on, how many, I could say I'm going to ignore all forces that are less than some amount or whatever. And then I can just theoretically begin to estimate how far my deviation is going to be. Let's compare the situation to quantum mechanics. Okay. If you give me a system, an open system in front of you, and it's an open system, what is its dynamical rule supposed to be? In general, there is actually no dynamical rule at all. There is none. This is true even if I have a closed system it's inside of. And even if I know the Hamiltonian of the closed system, there will be no rule at all for the subsystem. None.
But Jacob, there
Yeah.
will be a rule if I suppose that the subsystem state is separable from the state of
Yes.
the rest of the world.
Contingently.
Okay, wait.
Yeah.
But that seems to me exactly analogous to supposing that in the Newtonian case, the influences of other distant parts of the world, I can safely assume to be minimal, or something like
Okay, but so the confusion here is, again, I have two models. One is the way things really are, the facts of the matter, and then there's my idealization. In the Newtonian case, I have both of these things. I can believe that the object in front of me, there's some fact of the matter about the forces on it, its state, what it's going to do, and then I have my idealization of it, and they both live within Newtonian mechanics. In the quantum case, you're right. I can make idealizations. I can assume as a simple idealization that the initial state of my system cleanly factorizes off of its environment. I have my idealized model, and that will have some dynamics. It'll have some rules. But it's not approximating any dynamical model for which there's a fact of the matter. The open system, right, without those idealized assumptions, the open system doesn't have laws. So let me make, again, clear.
Okay,
Yeah.
let me.
In
Oh,
the,
wait, Jacob.
yeah.
Um, um, I thought I asked a straightforward, regular guy question, and I'm not sure what answer I've been given yet. Here's the question.
Yes.
Again. Is it part and parcel of what you mean by a realistic scientific description of the world? Okay, that it is committed to the claim that there is invariably a determinate fact of the matter about the physical situation of existence in its entirety, okay, in its principled entirety, and that the task of physics, the fundamental task of physics, is to describe how that state of that entirety changes, and then we can derive everything else we want from that. Is that your picture of a realistic theory?
Here's what I would say. On
That's not a yes or a no.
the answer is nuanced.
Okay.
If we're taking a metaphysics in which we believe that there is a maximal system that's well defined,
Uh-huh.
then yes, I would prefer physical theory, and I would say it is an ideal feature of a realist physical theory that it would be able to give us a description of that. But this is contingent on whether that is metaphysically the case. So, and here, so the only reason I brought the quantum mechanical example was just to show that there is already a problem in quantum mechanics with this, where we need to go to have any dynamics at all, we have to go to a sufficiently big system. And then this question of like, how do we know that such a big system exists? In the language of the metaphysics of mereology, we would say, how do we know that it is necessarily the case that there is a so-called mereological top system or universal fusion? People have different language for this. And it turns out this is actually a very delicate question.
How about saying it in more pedestrian language, more pedestrian philosophical language? There is an entirety of existence, okay? And what our fundamental theory is fundamental.
Wait, David, how do you know that?
Hmm?
How do you know that there's an entirety of
I don't have a proof of that, and that's part and parcel of my not having a proof that realism is true. I mean, maybe we're just having a semantic argument here.
I'm not sure it's semantic.
But,
I think it's substantive. Yeah.
okay, but
Yeah.
but I mean, there is a um I don't know what to say. What I'm used to wanting from a realistic theory, okay, what I get from Bohmian mechanics, what I get from Newtonian mechanics, what I get from the GRW theory, so on and so forth, is an account of the history of the entirety of physical existence. Of course, that takes it for granted that there is such a thing as the entirety of physical existence. If somebody has a good argument why there couldn't be an entirety of physical existence, why there couldn't be such a thing, why the very notion is incoherent or something like that, that would be interesting. And that would constitute, I would say, a serious challenge to the way we've traditionally understood realism. Okay. But in the absence of such a principled argument, I should think that it's a pretty straightforward demand on any scientific account of the world that I would consider that I would be interested in giving the label realistic to, that it constitutes, among other things, and not only among other things, but as it were primarily and in the first instance, okay, an account of how the entirety of physical existence works.
Yeah. So again, we're so I don't think we have like a semantic dispute, but I'm basically saying that I agree with you. I just don't want to engage in too much a priori metaphysics. That is, Newton's theory has the nice feature that you can be agnostic about whether there is a complete universe, and the theory still works just fine for open systems. And what's interesting about
When you say you agree with me, does that mean that it's gonna be fine if we go on with this conversation, assuming at every point that that is true? That what we have, what we need,
yeah, no, that's fine.
adequate.
If
Okay,
we're going to take this
so your
discussion that we
theory. So
believe there is a mereological top system, then yes, I would say that I would prefer when I talk about a realistic theory that it be a theory that give a
good.
description of that.
So I'm right in reading your theory
Yeah.
that way, as a theory of the top system.
Yeah, if there is a top system, then we can describe it, but I see it as one of the advantages of the theory that, like Newtonian mechanics, we don't have to make that a priori assumption. I don't know how to do Bohmian mechanics or Everettian mechanics or any of these other theories without something like that assumption. That worries me about those theories.
I have to say that I don't know how to do Newtonian mechanics without that, but we've been back and forth about that a little
That's
bit.
fine. That's
Okay,
fine.
that's fine.
Yeah, so we're in agreement, actually, I think. Yeah.
Okay, so if we're in agreement about that, so then we don't need to debate about that anymore. That's what we're talking about here. A theory of the top system from which all of the features and evolutions of the lower down systems can be described, can be deduced.
Yeah. I'll
Right.
just say that if people listening are interested in learning more about these questions about whether there's a mereological top system, in the terminology introduced by Jonathan Schaffer in 2010 is this question about, can there be so-called junkie systems? There's a really beautiful paper by Thomas Mormon, 2014, called Set Theory Topology and what is it? Set Theory and Topology and the and I think the possibility of junkie worlds. I think that's the name of the paper. And he has lots of very simple elementary examples for where you have simple, sensible mereological systems, notion systems where there's things that are parts of other things, where there just fails to be a top system. So that's all fine. But let's put that aside. If we're, for the sake of argument, going to take for granted that we can assume there's a mereological top system, then I'm happy to proceed. And the claim would be that this theory could accommodate that. Yes.
Good. So then, well, I don't want to direct, but maybe this will help me. My thought is that if it's conceded, for the sake of this conversation, that there is a top system, okay, then what I said about your laws constraining the dynamics no more than the bell jumping around theory does, or maybe I should put it as a question.
Yes.
Assuming that there is a top level system,
Yeah.
was I wrong to think that your laws don't constrain the dynamics any more than bells jumping
Yeah,
around?
that's the second point. So the first point I made about the theory is, and just to reiterate, systems have configurations in a configuration space in something like physical space. That was point one. Now point two. There's more structure than in the version of the theory that you presented. And again, this is a point where I'd say I had always implicitly assumed we had this structure. I agree that I wasn't as clear about it, and conversations like our discussions have helped me see that and be more explicit. So the second point is there's some more structure. There's modal structure. There's probabilistic structure in this theory. And there has to be, because we need probabilities to sew things together. Here, I'm very much motivated by my older work on the modal interpretations, which suffered from a lack of this structure, and from the Erhardt question mark theory, which lacked this structure. This sort of connective tissue connecting one time to another that lets these wild fluctuations happen. We don't like that. Okay. So here's the second point. What I'm saying is that each system we want to consider, whether it's open or closed, in addition to having configurations, forms a stochastic process. Now, a stochastic process is a fairly old idea. Stochastic processes go back the better part of the century. What is a stochastic process? In general, a stochastic process, I can give you the mathematical definition, but I'm not going to do that. It won't be interesting to people. One way to think about a stochastic process is it's some kind of variable, maybe representing the configuration of something. And this variable changes probabilistically with time. And this model comes with modal structure meaning like structure beyond just physical, like ontological facts at locations in space, like other structures. Modal structures include things like probabilities and laws and so forth. There's more modal structure here. These stochastic processes come with probability distributions over multiple times, right? So the model comes with a probability distribution that the variable is some value x at a given time. It comes with a probability distribution that the variable is x at a certain time and y at some other time. It comes with the probability that the variable is x at a given time, y at a given time, z at another time, and so on and so on. There's just this tower of so-called multi-time joint probabilities, just, where the system is. That's a lot of additional structure. Now, often simplifications are made when stochastic models are used in practice. We assume that a lot of that extra structure is somehow trivial or ignorable, and we get a very simple kind of stochastic process called a Markov process. The characteristic feature of a Markov process is that you just have to know what's going on at one time, and then you have probabilities that tell you what happened later, and the past is ignorable, and it simplifies these stochastic processes to assume they're Markov. Now, I say a little bit about why you might want to go beyond Markov. There's like many different reasons in recent years that have pointed to something very deep and intrinsically non-Markovian going on in quantum mechanics, even separate from the kind of prosaic violations of Markovianity that come from systems being open. There's like situations which even closed quantum systems seems to exhibit various forms of non-Markovianity. But in any event, a generic stochastic process will not have those simplifications. There'll be a huge assortment of these higher order probabilities. And you can understand why physicists have not been terribly interested in touching these theories with a 10-foot pole, because it seems like if you were to somehow take all of those multi-time joint probabilities to be laws, it would be a huge amount of information you'd have to specify. In principle, an infinite amount of information. And we don't want laws that are infinitely complicated. You end up...
Wait, Jacob, I'm getting lost again. Let's go to a very simple case. Once again, we consider a world which in its entirety is a collection of particles with positions.
Yes.
Okay, at every time.
Yes.
Good. I described a law that gives the positions at any time, the configurations at any time, assigns a probability distribution to the configurations at any time as a function of an initial configuration.
Yep. Yep.
Was that law false or incomplete?
Incomplete.
So say a little more.
Incomplete. So stochastic process has a lot more probabilities in it than that, a lot more joint probabilities. There are probabilities, given that the system is in X at configuration X at one time, and that it's at Y at some other time, and it's at Z. There's all these additional probabilities that do something. They're doing work. So it's not just that there's just sort of disconnected standalone probabilities every time, or even one conditional probability at some initial time t0 that gives you a conditional distribution over all the times and nothing else. For a generic stochastic process, they're going to be way more probabilities.
Yeah, but I'm not interested in the generic stochastic process. I'm interested in the theory you can
right, but that's just step
in
2.
order to reproduce the predictions of.
I understand, David, but I need to first of all say what a stochastic process is, because I'm claiming that quantum systems are stochastic processes. That's all I needed to say. The stochastic process comes with some collection.
Is the claim that quantum systems are stochastic processes a way of negating, a way of saying that the way I described your theory was false?
Yes, that it was incomplete.
Oh, okay.
Yeah.
Good.
Yeah, there's more. The way you described it had too little modal structure. There's more modal structure in the theory.
Oh, wait. So the probabilities are something other than what I said in that initial introduction?
The only
Probabilities are
probabilities
numerically different from the ones that I specified?
So you specified some of the probabilities, but there's more. And those other probabilities are doing work.
Give me a simple example of an additional one and of how we calculate it in your theory.
That's the next step.
Good.
So now that I've told you the ontology and I've told you that it's some stochastic process, which means that in principle there are all these like 2 and 3 and 4 time joint probability distributions. That's a lot of modal structure, and you might think this theory is non-predictive. Okay, so now we have the third step. Okay, here's the third step. The third step is we imagine, and here like explicit models can be written down. So this isn't just speculation, but you can imagine you take one of these stochastic processes. It's not Markov. It's got all these multi-time probabilities. We don't know what they are. And you imagine that there is some particular time, t prime, call it time t prime. And at time t prime, something interesting just happens with this theory. At t prime, among all the probabilities this system has, it has many, 2, 3, 4 time joint probabilities, conditional probabilities, all that. At this time t prime, the first order conditional probabilities, that means that among all these probabilities, the ones of the form probability the system is at x at some time t, given that it was at y at time t prime, those probabilities, and those are called rooted at t prime. That means they're conditioned at t prime. They're rooted at t prime. Suppose there's a time t prime at which those first order conditional probabilities become independent of the standalone probability distribution at t prime. Okay, so there's a sequestration between these first order probabilities and the standalone probabilities of t prime. That means, just to make this super clear, what I'm saying is there's a time t prime at which On the one hand, we have the standalone probability distribution, just unconditioned, the probability of what configuration Y the system is in at T prime. And we have a conditional probability, the probability that it is X at T, given that it was at Y at T prime. We have these two things, the standalone probabilities and the conditional probabilities, and they neatly separate. The conditional probabilities do not depend on the instantaneous conditions at T prime anymore. They
Do you mean that the dependence is exactly zero?
no,
Or
let me come back to that in a moment. It's not exactly zero, but let me come back to that because it's very important, okay? Let's suppose just for the second that it's zero, but then I'll come back and explain what we don't need to be zero. If it were exactly zero, what we would suddenly have in this model is what we call in the philosophy of physics parlance, a good initial value problem, with a clean separation between initial conditions, just meaning the instantaneous conditions at T prime, in this case represented by the standalone probability distribution at T prime, on the one hand, and then separately, a dynamical law in the form of first-order conditional transition probabilities rooted at T prime that tell you, given the system's configuration at T prime, this is the probability distribution for what its configuration will be at any later time T, what configuration X will be at a later time T. This is now a good initial value problem. You can counterfactually imagine different probability distributions, standalone probability distributions T prime, and counterfactually altering them. You've got a dynamical law that then projects those forward and tells you what's going to happen. That's what a division event is. Now, if division events are not exactly perfect, all that means, it doesn't mean that we had nothing and that there's no modal structure and everything falls apart. It just means that the initial value problem is slightly imprecise and that the behavior of the system will deviate ever so slightly from the predictions that you make if you assumed it was a perfect initial value problem. Now, to be clear, these division events, as I prove in the paper, they emerge out of decoherence. And so the discrepancy...
Not exact ones, of course.
Not exact. No,
Right.
not exact.
Right.
But they're exact to like 1 part in 10 to the 40. I mean,
Yeah. But that's not the...
But the point is, it's not that without them, the system has no modal structure. This is the key thing.
That's what I'm not understanding.
Yeah.
So look,
now this is akin to the Newtonian case where there's like an exact statement of what the forces are that we don't know. And yet there's something that really does happen. And then there's our idealization that we can make predictions with, and there'll be tiny discrepancies. This is exactly the same thing.
Jacob, look, you got to help me out a little.
Okay, yes.
I gave in the beginning of my remarks, a 1-sentence complete statement of a theory of the entirety of physical existence. Okay. Now, maybe that theory was wrong. Maybe that theory was not the one that you intended.
Right.
Okay?
It's
Good.
not. Yeah.
It is a theory that's going to be, in this trivial and useless sense, empirically adequate in the way that the bell jumping around theory is, and so on and so forth. But good. What you need to give me, I don't think it's going to help me to hear a lot of stories about all the varieties of stochastic dynamics there are, and so on and so forth. Can you give me a succinct statement like F equals ma in the Newtonian case, or like the statement I gave you in the beginning of my remarks about what, on your picture, the complete laws of the world are? I gave a succinct statement of those. I gave it in 1 sentence. I was proud of the simplicity of this 1 sentence. It's clear that your reaction is, no, that's not my theory.
Right.
Good. Is there a theory? Is there a way of stating what your theory positively is that rivals my statement for succinctness?
I mean, as long as I'm allowed to assume that people know what a stochastic process is.
No, you're not. No, I didn't.
Well,
I didn't assume that.
Well,
I gave such a simple claim Okay.
But
I
the
gave
claim
some
is that the
simple
universe is a stochastic
here's
process.
the
I
initial
don't know how to.
configuration of the world.
Yeah.
Here's how you calculate the probabilities of future configurations. Period. End of story.
Let me try my best here. Okay.
Okay.
So there's a set of possible configurations of your system.
Yeah.
There is, as part of the theory, although we don't have epistemic access to it, a whole bunch of joint probabilities for all the goings on of the system. And at certain moments, these division event moments, the T primes, we get a nice emergent initial value formulation where you can imagine
So what
counterfactually
are the
changing the
rules?
initial conditions at that time and then projecting them forward.
What are the
That's
rules of doing the calculation?
what
What are
say
the
what?
rules for calculating all these probabilities?
Excellent. That's the next point. Good. So there are two nice ways to think about this. The first is very general. If you have one of these division events just spontaneously
Oh,
occurs,
wait. You got to tell me what a division event is. A division event is not an exact division event because
it
those.
doesn't have to be exact. No.
What does it have to be?
It just
We're
has to
talking
be
about
really good.
We're talking about fundamental laws.
I understand. There is a fundamental description. If you want a so-called, there's an exact description in which what we have is a configuration of the system changing in time and a bunch of multi-time joint probabilities capturing what it's doing. We don't
All
have
right,
access to
good.
that.
And we shouldn't have to talk about anything else but that.
That's fine. That's fine. That's
Good.
good.
Tell me
But a
how to
system
calculate.
like this will simply, in the generic case, occasionally have times where things simplify.
But forget about that.
Yeah.
Just tell me what the basic universal rules are.
I did. That's the rule. The rule
What's
is
the
that
rule?
and then in some situations, they'll
Wait,
simplify enough that we
no.
get a good initial value
Start at the
problem.
beginning of a sentence. Don't say "and then in some situations." What's the rule?
So I think you may be thinking a little too narrowly about rules. I'm
Maybe
saying that
so.
what nature is a stochastic process. That means that there's configurations and there's also probabilities. And in general, that's all you got at a fundamental level. But so the question is like, where are the laws? Where are the laws? For a completely generic open system, not a division event, there aren't any. This is the structure you've got. Now, what can happen, and of course, what you have to assume, the past hypothesis of this sort of picture, is that there was a time, T naught, if you will, where that complicated set of probabilities has this nice feature that at T naught, we get a nice separation between the standalone probabilities and the first order transition probabilities, the first order conditionals that are rooted there. And we assume that happens. We don't assume it happens anywhere else. But here's what's really cool about this. If there is such time, then there's a simple mathematical transformation you can do that turns this whole system into a Hilbert space description. Not only a Hilbert space description, but it turns out you can represent how the system is behaving using unitary time evolution operators, all the usual familiar appurtenances that we know and love from quantum mechanics. And so as long as there's one such moment, we're going to have something like a representation in which we have unitary time evolution. Now, here's the next thing to say. If this system is really big, and again, you can construct very concrete models of this. One of them is constructed in the paper. If you had a big system with lots of degrees of freedom, that just means its configurations are very complicated, a lot of moving parts. We could talk about subsystems. Subsystems would just be some sub-collection of those degrees of freedom. If you imagine that the overall structure of this whole thing, the Hamiltonian, the unitary evolution, whatever, you set it up so that something like a measurement-like interaction takes place. Now, I say the word measurement. I'm not treating measurements as primitive. Just two systems happen to bump into each other, and the configuration of the one very closely, changes in a way that corresponds to the configuration of the other. Just two systems being treated as part of this overall system. What you can show, and this is done explicitly in the paper, is that when that happens, the marginalized probabilities for the subsystem being measured, its own marginalizing over the environment, its own probabilities, which in general are just going to be all over the place, multi-time, whatever, they will develop a division event of this kind. That is, when that interaction happens, the subsystem being measured
Yeah,
will
but what if
suddenly
you look
have
at
a
the whole
clean separation between its standalone probabilities at that time and the first-order conditionals. And that means that we have an initial value problem at that moment for that subsystem. It arises emergently. So what you're looking for,
this
David, is
level of accuracy?
sure. This is so what's exact is the configurations and the modal structure. What's inexact are the emergent dynamical laws and initial value
But I
problems.
don't want the emergent dynamical laws. I want the fundamental dynamical laws.
I think so. This is, I think, where there's a substantive metaphysical difference between us,
Uh-huh.
and that's fine. I
Okay.
don't think that at the end of the day, on a theory like this, we're going to have as a fundamental statement that there is just some initial value problem phrased in terms of dynamical laws that take the form of conditions on freely adjustable counterfactual initial conditions as a general statement.
So
What I'm proposing is that there is a more primordial modal structure from which that picture of dynamical laws and initial value problems emerges to a very good approximation in various circumstances. And I see this as an asset in the sense that we explain what is a mysterious fact about the nomological structure of our physical theories. I mean, one big question that people have had a long time is, why do our best physical theories have this clean nomological or law-like structure? We have this nice clean separation between initial conditions and dynamical laws. Here I'm giving you an account with a much more primordial structure, modal structure, from which that clean initial value formulation with clean laws separate from initial conditions emerges to a very good approximation in real-world cases. So I'm trying to get at that structure from a more primordial structure. And my argument is that in order to get quantum mechanics to make sense, we have to make that move.
Um, um, well, in order to make it make sense without a wave function, we've got
Sure,
other ways of making it make sense.
sure, yeah.
But anyway,
Although I would argue you can't make sense of it with a wave function anyway. So I wanted to get to this also. It's not just that I think that
but
this.
wait, just hold on one second before we move on.
Sure.
Look, um, I started out my little remarks by apologizing profusely about how much they were going to take for granted in terms of the knowledge of the listener. But I mean, you're going way beyond that. Okay. It feels like I'm asking a very flat-footed question. Okay. I shouldn't be asking things then. If I hear you, I shouldn't be asking questions like, what are the fundamental dynamical laws, or what are the fundamental laws under which the
What
probabilities?
do you mean by laws?
I mean, do you want to get into a whole Jungian?
Not the metaphysics of laws. I don't mean like our laws Humean. What I
So,
just mean is,
what are you asking?
do you think that
Here's the picture that I had. Okay.
yes,
Um,
we need initial value formulation. In other words.
you
Is that
have a law.
necessary?
Well, I don't know if it's right to call this an initial value formulation, because it doesn't assign states at every time.
I'm asking
I
you if you think it's necessary for laws that there be an initial value formulation.
No,
Do you
no,
think that's a
no.
necessary condition?
It depends what you mean by an initial value formulation, but I'm pretty sure the answer is no. It's fine with me if you have other kinds of boundaries. You know, there are laws of electrostatics, okay, which have boundary
I'm
conditions
sorry, boundary. Do you
that
believe that it's
don't have
necessary
any
that laws be
particular
dividable into
well,
boundary conditions? Yeah.
but that doesn't have to be that either. I mean, F equals ma doesn't refer to particular boundary conditions unless you're setting up a particular way of solving it. So no, there's no attachment to anything like that. I just want to know exactly what it is, and I'm hoping for a simple statement of it, like the one sentence statement I gave of what I took to be your theory in the beginning of my presentation. Okay. I want some kind of a simple claim, okay, about I don't know how to put this generally, sufficiently generally. No, it certainly doesn't have to be an initial value formulation. I don't even see why it has to be a boundary value formulation or something like that. But some simple statement of exactly what the rules are that determine which histories of the world or which totalities of the world are physically possible and which are not.
The
Okay.
rules are
Get there, and in other versions of quantum mechanics, and in the version of quantum mechanics that I proposed for you, there turned out to be a very simple such statement. So far, I'm not hearing a statement like that from you.
yeah. So the rules are the universe is a stochastic process. That's the rule.
No, but Jacob, that's not enough.
That,
There are
okay.
lots of those.
Yes, there are. Yeah.
Good. What are the rules of this one? What are
It's
the
gotta be really
rules?
big,
Yeah,
and we assume at some in some time, the past hypothesis is there's some time in which we get this clean separation. We
that's it.
get an initial value problem at some time.
There's nothing of a dynamical nature, not that there has to be, but I'm just asking, is there nothing here of a dynamical nature? I thought there was a dynamics here, but it was non-Markovian. You're telling me, no, 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 there's no dynamics. Dynamics is not the right way to think about it on the fundamental level.
So,
Sounds like you're saying.
yeah. So, if you take a non-Markovian process and you imagine all the probabilities of the form, what's the probability my system is in configuration x at time t, given where it was at time 1, given where it was at time 1 and where it was at time 2, given where it was at time 1 and time 2 and time 3, and so on and so on and so on, you'll get a tower of conditional probabilities that you can think of as the dynamics of the non-Markovian process. And those are the dynamical, those would be something like dynamical laws for the non-Markovian process. So if you want, that's the laws, right?
I'm still okay. I shouldn't. I'm sorry. I'm prolonging
No, but this is actually very good.
what may not be useful.
I'm making a posit about what the structure of the world is like. I'm saying that the world consists of configurations of things that change with time. And
Okay.
there are probabilities that
Wait, wait.
systematize or
The
describe
world
those.
consists of configurations of things, and those configurations change with time.
Yeah, the
And
configurations change with time, but those changes with time are systematized by some set of
no,
joint
no, no, no.
probabilities.
Good.
Yeah.
Those configurations change with time.
Yeah, they do.
Wait. Let me finish a sentence. Good. What I'm used to thinking I'm going to be offered by fundamental physical laws about worlds like that is some claim like, here is the set of evolutions of these configurations that are physically possible, and here's the set that aren't. Okay. I'm used to being offered some simple rule which distinguishes between those two. It sounds like you're telling me that's not what I should be hoping for.
Well, I mean, you'll have probabilities that are higher for some things happening and lower for other things happening. And probably there are some things where the probabilities are negligibly small. We would say those don't happen. But yeah, I'm giving you that structure. I'm saying that there are probabilities over all the, joint, whatever, configuration system. And some of them will have very low probabilities. Some will have very high probabilities.
No. But say in the GRW theory, you don't have deterministic claims of the form, this sequence of states is physically allowed, that sequence of states is not physically allowed.
Oh, the GRW theory is probabilistic. So
Yeah, that's what I mean.
yeah.
But
You're not going to have a clean thing where you say these are definitely impossible and these are
no,
possible.
that's right. But what you do have, okay, are claims about, are the kind of thing that you're calling an initial value problem, okay?
Right.
Or
GRW has an initial value problem.
right.
Yeah.
Or initial value formulation.
Initial value formulation. What I'm saying is we can take an initial value formulation at T naught to be our past hypothesis, if you will, to get the ball rolling.
Wait. Take an initial value formulation or a claim about the initial value to be the past type.
So if you want both, I mean, in the Mentaculus, there's both a statement, the past hypothesis about the macro state being low entropy, and also there's the statistical postulate about, the probability distribution over initial microstates. In this case, to get the ball rolling, you need there to be a T naught at which you have an initial value formulation. You can then argue, well, okay, now that we have this initial value formulation, we can then maybe ask, okay, what does the initial distribution need to look like? And we might impose something like the statistical postulate on that
Yeah, yeah.
initial.
No. I'm sorry. I'm dragging us off the point here. Um, um, Look, I'm on this topic here. I feel a bit lost at the moment. I don't understand what it is, what set of claims it is that your theory is making about the entirety of what exists. To say that it's a stochastic process isn't enough. I want to know which
That's yeah. So
I want to know, in the GRW case, I have precise, extremely simple rules saying which evolutions of probabilities are physically possible and which are not. Okay.
okay,
It doesn't sound like I'm going to get something similar here
let me
on a
yeah.
fundamental level until I have a division event. Okay.
Let me try. Well, I think maybe this will work a little better. Let's make the following stipulations. Okay, configurations, stochastic process, and there's a T naught, a time T naught, in which the stochastic processes we're going to consider are all going to be ones at which, at this time T naught, there is this clean separation between initial
What do you
conditions.
mean by the ones we're going to consider? You mean the entirety, the ones that concern the entirety of
Yes,
existence?
yes.
Oh,
If you want,
so this is exact.
yep. Well, I don't know if it's exact. It could be. It might not be. I don't know if it
You
is.
give it to Jacob.
No,
You're
but you see, no,
making me
my
nervous.
point is, I'm not going to
Yeah.
make an a priori statement
No, I'm not
that it
asking you to
must be
make an
exact.
a
It could
priori
be.
statement. There is so far the game of fundamental physics has been played within the context of what I'm calling this realistic assumption that there are these facts about what the entirety of existence is doing.
Yes.
You say we don't have a proof of that.
No, David. It's not what I'm saying. That's not what I'm saying. I'm saying the facts that you're referring to are facts about configurations and joint probabilities, and I'm saying those are facts. But what you would like is something more than those facts. You also want some kind of additional thing, and I'm saying that it. So I'm a realist here in the sense that I'm saying, like, there are configurations at all times. There are joint probabilities
There are configurations of everything
of everything.
at
Yeah.
all times.
If we're going to take for granted there's a mereological top system, that's
Yes.
a system of everything.
Yes.
I'm saying on this theory that top system has a configuration at every time, and that there are joint probabilities of what its configurations are at all times, and those are all statements about what this thing is doing.
And
They're
in
all
the
behavioral
evolution of
statements.
that top system,
Say what?
right? And in the evolution of that top system, are
Yes.
there exact division events?
Maybe, maybe not. I'm not assuming that there are. They could be, but I'm not requiring it.
It seems like
No, I'm not
we
requiring
have
that there are. We have a well-defined behavior, and I am assuming that there's at least one that's very, very good. And from that very, very good one, we get a nice, clean
very,
initial
very
value
good.
problem that we can use to make prediction.
Okay.
That's what I'm saying. Yeah.
Okay. I feel like I'm not being helpful here. I'm just lost. I would have, like I say, here's something which, if you're inclined to think about it, would be helpful. If my initial statement of the fundamental laws of the world on your picture was false, okay, give me one that makes predictions that the theory you actually believe in it's numerically different from those. False in that very flat-footed sense. If it's false, it would be great to have a simple statement of what's true that rivals in simplicity the statement I gave, which you're telling me is false.
So it's false in the sense it's incomplete. It is the case that if I give you a stochastic process for a mereological top system, it is the case if I give you this, and if there is a division of n at T0, then it will be the case that among the modal structure will be the probabilities you were talking about. Conditioned at T0, such and such with the probability later times. That will be among the probabilities, but it
Good.
won't be the
Now,
only
I
probability.
gave a crisp prescription for calculating those probabilities.
Yes, yes.
What's the prescription for calculating the other probabilities that this one leaves out?
Excellent. So in general, we won't have epistemic access to all of them. They'll be beyond our ability to
I'm not
measure
worried
or
about
know. But what you can show is that if you have all that extra structure there implicit, even if we don't have epistemic access to it, then what it will entail is that subsystems bumping into each other will develop their own initial value
But
formulation.
what determines what are the rules of the extra structure? I gave you the rules of this of these probabilities of configurations at any one time. It's the Schrodinger equation and the Born rule. Period. Okay. What are the rules that determine the extra structure?
If you take an initial division event, put a Hamiltonian there,
No,
and that
but
Hamiltonian...
Jacob, I get so queasy when your answers start with if. I'm asking an unconditional question. What are the
I don't
rules?
think there are answers to all questions are conditional, right?
I come on.
No,
No.
okay. Look, what
Yeah.
you're demanding is a level of simplicity
Mm-hmm.
that is not going to work.
I
It's not
see.
available. And I want to make very clear here, and I want to pivot a little bit because we have more to talk about. We're going to have to give something up. What I'm giving up is exact initial value problems. That's what I'm giving up, but I'm not giving up modal structure probabilities. Now, what I've argued is that we have no other theories on the table that are going to work. And I want to talk a little bit about why that is.
We have Bohmian
We
mechanics.
don't have Bohmian mechanics. No, David, we don't. We have Bohmian mechanics only for systems of fixed numbers of finitely many non-relative.
No, I don't agree with that. But that's another story.
No, this is actually very important because if you think that there's a way out of this, you'll be like, well, why do we need this crazy idea?
We have a suggestion from Bell
Oh, we
about
do.
this. Yeah.
You're referring to Beables for quantum field
Sure.
theory, 1984 paper.
Yeah.
Unfortunately, it doesn't work.
What do you mean?
Okay. So I have to tell a little bit of history here to explain why it doesn't work. This is actually really important, and it's not widely known. So for the background for the listener, Bohm's theory is when you're dealing with, non-relative particles, it's deterministic. But when you want to generalize the theory to handle fields, it's a little complicated to do for all kinds of reasons. And so what John Bell proposed in 1984 was a stochastic jump model, a Markov-type jump model, where the number of particles and their locations, at least for fermions, they jump around kind of in a stochastic way, probabilistically, but in a Markov way, in the sense that you only need the initial wave function and the initial state, and then you get what comes forward. As best I can tell, this idea was basically accepted broadly as, well, it works, the equations look fine. In 1992, there was a paper by Lucian Hardy, at the time he was at Durham, and Home and Squires and Whitaker. And it was called something like Realism for the Quantum Mechanical Two-Level Oscillator, something like that. It was in Physical Review A. I don't think they knew about Beables for quantum field theory, or at least it wasn't cited in the paper. But what they presented was a simplified version of Bell's proposal for a two-level system. Bell was dealing with an infinite level system.
Mm-hmm.
Hardy et al. Proposed the exact same model, but for a very simple two-level system. Today we would call it a qubit, but the term wasn't available yet for reasons that Robinson and listeners may remember. We talked about the etymology of qubits. The word qubit wasn't available. They called it a two-level system, but it was basically a qubit. And they said, can we account for what we see in the quantum mechanics of a qubit with a stochastic jump model? It was the same as Bell's model. And they wrote it down. They wrote the equations. The equations are very similar to Bell's equations. You get a master equation, you get all this stuff. 2 years later, Daniel Gillespie, who I don't know if that's a name that's familiar to people here, he was a master stochastic theorist,
Mm-hmm.
responsible for, among other things, the Gillespie algorithm, which I think is like 13,000 citations. He wrote books on this. Anyway, he had an interest in quantum mechanics. And so he read this paper and he said it doesn't work. And because this is a simplified version of what Bell was doing a fortiori, Bell's model also doesn't work. And so he wrote an article explaining, and the title of the article was 1994, also in Physical Review A, not widely known, not widely cited. But the title of the paper is Why Quantum Mechanics Cannot Be Formulated as a Markov Process. That's what it was called. And he said, the mathematical equations are great. They look perfectly beautiful. You took quantum mechanics and you tried to write down these equations that formally resemble the equations of a stochastic process, a Markov process. But they couldn't actually describe an actual Markov process. Some things were lost in translation. If these equations purportedly describing a Markov process really were describing a Markov process, and all the ingredients really had meanings that you would give them if this were really a Markov process, then mixed into some of those mathematical ingredients would be various additional probabilities, various additional, transition probabilities and stuff. And what Gillespie showed was that some of those probabilities failed to stay between 0 and 1. Now, if you weren't paying attention to this, and Bell certainly didn't pay attention to this, there was none of this in Bell's work, you got to make sure that every little quantity that's going to end up being something like a probability stays in the right bounds. Bell didn't check that. And what Gillespie shows is some of them diverge enormously. Don't stay good probabilities between 0 and 1, and so this couldn't possibly be coming from a Markov process. Gillespie wrote this paper, and he had a couple of other criticisms. There's a variety of problems that show up. And then Hardy and his colleagues, they wrote a paper, it was published in 1997, responding to this. It was reply to Why Quantum Mechanics Can Be. And then Gillespie wrote comment on reply to, also 1997. And then it basically just petered out after there. These papers have, I think, I think Gillespie's articles got like 8 citations. Basically, no one saw them. But you can read them, and they are pretty devastating.
I should.
Yeah, they're worth reading, and I recommend. Unfortunately, Daniel Gillespie died a few years ago. I think he had brain cancer. It was very unfortunate. Now, what did this lead him to? Interesting. Remember, I told you how roads keep leading to non-Markovianity. So what Gillespie decided to try a few years later was to see if he could build a non-Markovian stochastic formulation of quantum mechanics. And he attempted to do this in a couple of papers in 2000, 2001. He gave up. He didn't know how to make it work. And, I'm both very grateful that he tried to do it and also grateful that he didn't succeed, because then I wouldn't have had anything to do. But it's worth noting that one of the world's great historical stochastic modelers looked at not what Bell was doing, but what Hardy was doing, which is a simple version of what Bell was doing, and said this is not really a valid
well, look,
process.
Needless to say, Jacob, this sounds very interesting.
It's very interesting, but it also means we lose that as an avenue.
Look at it. I have no idea what to say about it off the top of my head.
I wouldn't, these little-known papers, but I'm just saying, if your thought was, well, why do we need this? We can't always go to be able to
even if all of this is exactly as you're reading it, there's no argument that this is the only way to Bohmi's quantum field theories, that is Bell's way. That is, even if everything you're saying about the way Bell fails is taken on board, there's no reason to think that's the only available route to Bohmising field theories, quantum field theories. But anyway,
I would view this as the way to do it. Basically, if you take Bell's approach, which was Markov, and show that it doesn't work, you could say, well, is there a non-Markovian way to Bohmize?
Or is there an altogether different approach? But
my approach is the non-Markovian version of what Bell was doing.
And I think Bell also mentions in this paper, you could do it deterministically with non-fermion fields. Okay. And it might be, for example, that knowing the value of the gravitational field everywhere in this room is enough to tell me where the tables and chairs are and so on. And maybe that's all I need from such a theory. So there are Bell didn't go very far with this. There are lots of approaches. The stochastic approach you're mentioning is not the only one that he mentions, even in that paper.
Yeah, and our friends, Shelley and Nino and everybody,
Right,
they talked about exactly what are the ontological commitments we need at minimum to get a
right,
realistic picture. Maybe
right,
we only need bosons. Maybe we
right,
only need.
exactly.
So
Right.
granted, right? I mean,
And you
I
have a completely deterministic theory, as in Bohm's non-relativistic quantum mechanical theory, yada yada yada. So there's a lot to say about that. Um, if the status of the discussion is obviously none of the existing approaches can work. If the status of the current conversation is obviously all of the existing approaches are at a definitive dead end, that seems wrong to me. Okay, and and uh, and then questions can arise. Okay, if they're not all at a dead end, how much would we be willing to sacrifice of what kind of thing, so on. Then we get into a delicate balancing act
yeah,
of the kind we've been dealing with for a long
but Dave, let me ask you a question.
time.
How
Mhm.
old is the Bohm theory at this point?
How old? I mean, it was first published in the 50s.
Yeah. Bohm started working on it in late 1951. He published it in
Jacob,
52.
how old was Aristotelian physics
No,
before
but here's
before
here's
we
my
did
point, right?
better?
Yeah,
You know,
but wait, David. And of course, if you go back to De Broglie's formulation in 1930, which was
right.
very similar to Bohm's theory, we're
Well,
talking about a theory that's
it's
almost
pretty
a
clear that
century old.
Debroy didn't understand his theory. That
His
Debroy
1930
was
book is
presented with objections to his theory, which he should have taken care of with a wave of the hand. Okay, and he sort of gave up.
so De Broglie didn't understand decoherence, which plays a very important role in Bohm's theory.
That's part of what he didn't understand. But my understanding was that Pauli pointed out to him that on his theory, an electron in a ground state orbital would be stationary, which is obviously preposterous. Okay, and De Broglie put his tail between his legs and whimpered off instead of saying to Pauli what exactly would be preposterous.
Yeah, what would be processed? But in Bohm's theory, that's what happens. Yeah,
Right,
no,
right,
I agree. De Broglie didn't have the courage of his convictions in 1930.
right.
He also didn't like the idea that the wave function lived in the configuration space. He was very worried about that. And he talked about what that, yeah. But he had basically the structure of the Bohm theory. My point is, um, it's not that there's a definitive argument that you can't possibly make something like deterministic Bohmian mechanics work, but it's been a really long time, and I'm not going to wait anymore on the hopes that that could happen. It could happen. People have been trying to get probability to work and have ready in quantum mechanics for over 70 years.
Right.
You know that you and I are both in agreement that that project is not going to succeed.
I think that's right.
Yeah,
Yes.
and so sure, there's the GRW theories which are not ruled out. And to be clear, I mean some of them have been ruled out, but there's still some live GRW theories. And I regard those as certainly possibilities. But I do think it is entirely reasonable at this point, well into the 21st century, that we should strike out in a new direction,
I
especially
but
if
but
there's
of
yeah,
course I agree with that, Jacob, and that was exactly the nature of my introduction.
right.
I was happy in the beginning because I thought I had an exact, simple statement of what it is that this theory asserts. Okay. And you're suggesting, one, that that was wrong, and two, that
Incomplete.
yeah, okay. And two,
Incomplete.
that there isn't going to be something to offer me along the lines that I guess I was hoping for. Um, I mean, mind you, given, mind you, given what I started with, my version of your theory, I don't think it's by any means at a dead end. One could experiment with adding dynamics to it, okay, in the way I suggested. The initial suggestion I had for adding dynamics to it was silly. We didn't talk about it here.
Yeah.
But there might be better ways of adding dynamics to it. There might be a lot to there might be a lot to say there.
Yeah.
Okay.
So, but let me just say that there's a version of the theory I think you'd be happy with, which is that there is a division of n at T naught, and you can take it to be exact. The David Albert version of this theory is there's an exact division of n at T naught. At that exact division event, because it's an exact division event, we can specify exactly by a formula, actual formula, what the conditional probability distribution will be at later times.
Mm-hmm.
But that's not all that the theory contains. It also contains all these higher order probabilities.
That which theory? That's not all that the theory. Take
David's theory.
take the theory as I stated it. Okay,
That is not that. So that's not a version of my theory at all.
fine. Is it a theory?
I guess it's a theory. It's not the theory that I'm proposing.
That's okay.
What I'm saying is there's a version of my theory called the David Albert version of
Right.
the indivisible theory.
Right.
That is the indivisible theory, and it contains among its ingredients conditional probabilities, conditioned, rooted at T naught to the future, but it contains more. That's all I'm saying. It contains
And it
more
contains
than
the
that.
rules of the Moore stuff.
Right. So the other stuff is not fixed by what we have epistemic access to. It's not fixed by the first order rules. We fixed the first order rules. The other stuff, I don't know what it is. But the fact that it's there at all has implications for what happens to the universe as a whole and to its subsystems. And this now just requires like working through calculations with stochastic processes. But if you assume all that stuff is there, even if we don't know what it is, and you assume that we've got David's law starting from T naught and going into the future,
Mm-hmm.
then you can do marginalization on those unknown probabilities, and the details you didn't know wash out of the predictions for subsystems. That's what's miraculous about this, is the washing out of the unknown details. So here's a version of this. It's not quite the same thing, but it gets a little bit about what I'm trying to say. On the non-relativistic Bohmian theory, there's a lot of information that we humans don't have epistemic access to. Now, the theory does stipulate what they are. Let me be clear. The theory stipulates what they are, but we don't have epistemic access to them.
Unlike in your case.
Right, exactly.
Yeah.
So we don't have access to them, and if we did, if we could somehow see all the hidden trajectories of the Bohmian particles, if we could somehow see them in some sense, sense them, we could sense them, then we could do all kinds of, send signals, and you could do all kinds of weird stuff.
Mm-hmm.
We don't have access to them. We can't have access to them.
Right.
Now, in the theory that I'm describing, we don't have access to the true trajectory taken by the system, just like in the Bohm case. We also...
Bohm case, the theory does tell us.
The theory, yes, that's right.
In
In this case, the theory doesn't fix what those higher probabilities are based on what we've specified. So your law about first-order transition probabilities rooted at T naught is not enough to fix what all that other stuff is. Now, the proposal is there is stuff there. It's just not fixed by the law you gave. And so you might ask, well, gosh.
No, but is it fixed by some other law that you give?
It's partially fixed, yes, and let me explain.
Is it fixed complete?
No, it's not fixed completely.
Okay, then
it's not.
then
all
I
that
don't
higher
know
stuff
what
is not
we're
fixed
talking
completely.
about.
In the sense that, like, the universe knows what it is, but we don't, is what I mean. So, we don't have epistemic access to it. The theory does not specify what it is.
Right. The first statement is true of Bohm's theory also.
That's right, but not the second statement.
Is false. Right.
This is different from Bohm's theory.
That's correct.
This theory does not. The theory doesn't fix what those higher order conditional probabilities are. And so your reaction might be, well, there's all this probabilistic modal structure that the theory doesn't specify doesn't fix uniquely. Can we say anything at all about it? And the answer is we can, because if your David's law, the one rooted at T naught, which is describable by unitary evolution, you can show it's describable by unitary evolution. If that evolution implies, and again, construct exact examples of this, that subsystems will interact in such a way to generate these emergent initial value problems, then that higher information we didn't have access to and the theory doesn't specify, it washes out.
Except if we're interested in the entirety of what exists.
That's right.
Yes.
If the entirety of what exists, the whole universe as a whole, we're not talking about macroscopic systems like you or me, or mesoscopic systems or planets. We want some statement about the entire universe as a whole. Can we fix exactly what the multi-time probabilities are for the universe as a whole? The answer is no. We can't fix those. However, the fact that we do get fixing of what's going on for subsystems puts strong constraints upwardly on those multi-time joint probabilities. So this is where you just get in the weeds of all these sort of calculations, but you discover that if there are subsystems that spontaneously develop division events and have nice initial value statements where there's a clean separation, you can show that that actually constrains what all those higher order probabilities could have been doing, but not completely. They are left somewhat unfixed. There may be a fact of the matter of what they are, but the theory doesn't tell you what they are. And this means that we have a certain degree of epistemic humility about what we can demand. Now, this might not meet your requirement for what an exact theory should be. You might say an exact theory should tell me exactly what all those higher order probabilities are, even if we don't humans have epistemic access to them.
As Bohm's theory does.
As Bohm's theory does, except that Bohm's theory doesn't handle the relativistic case.
No, that's not what I'm talking about here. Okay.
Right, but I'm just saying, like, you're right. It would be nice to have a deterministic theory in which the theory says it's the Schrodinger equation plus a guiding equation and all of that stuff. Be nice. Now, the other thing is that, of course, the Bohm theory has this wave function in it that we're supposed to somehow make sense of. Now, one of the things that led de Broglie to abandon his pilot wave theory, it wasn't the only thing, but it was one of the things, was that he was very clear he could not accept that there was an ontological pilot wave in many-dimensional configuration space. He is very explicit about this in his 1930 book. When Bohm independently resurrected the de Broglie theory, he was put into touch with Pauli, who issued the exact same objections. What do you mean, a physical wave in what he called polydimensional space? And Bohm, and I think maybe Bohm was the first. I can't think of anyone else who I know who is prominent. Bohm went all in. He said, that's just prejudice to say that a thing can't exist because it's polydimensional. I believe this thing really ontologically exists, and it really exists in a high-dimensional configuration space. And at least I'm providing you with anything, because the Copenhagen interpretation gives us nothing, and I'm giving you something. And they went back and forth about this, and Bohm went really hard on this. You see a little bit of this in, of course, his Bohm's two papers, his 1952 papers, but this is really much more well articulated in this correspondence with Pauli. And I recommend people who are interested. I have a paper called "Historical Debates Over the Physical Reality of the Wave Function." It's on, you can see it on Phil Sire on the archive, where I show you this correspondence. It's very interesting. Everett was heavily motivated by Bohm and this view of the wave function developing Everett in quantum mechanics, which also, on some views, takes the wave function, maybe not in configuration space, but maybe in Hilbert space, as being ontological. So if you want to go the Bohmian route, you're not just going to have to deal with all the problems we talked about. You are going to get trajectories. The theory is going to fix the trajectories, but there will be a cost. And the cost will be that your ontology is vastly larger because of this.
Oh, of course, Jake. This was, first of all, this was the ad for your theory that I started out with.
Yes.
And moreover, the business of what to do with this high dimensional object is something that's preoccupied a lot of my time for the past 15 years and a lot of books that I've written.
That's right. So, but let me give a different view on what this thing is. And this is now from a different paper. And you and I have talked a little bit about this. There were some very interesting developments in the theory of stochastic processes starting in the 60s, but really in the 70s and 80s. Some of this was not widely shared because it was coming out of the Institute for Defense Analysis. And this is people like Lee Neuwirth, and there's a bunch of people who worked on these things in the 70s and 80s. So totally inaccessible to people Bohm, this is decades after Bohm. But they basically noticed, okay, well, suppose you did have a non-Markovian stochastic process. Could you make it into something that looks like a Markov process? Could you just formally make it into something like that? And they discovered that there was a way to do that. The way to do that was to take all of those additional multi-time joint probability, all that stuff,
Yeah, we've talked.
and write it as a present moment new set of degrees of freedom. And they have characteristic features, David. Very, very characteristic qualities. One is there's a lot of variables you need. That's one. Another is they're abstract. They're usually phrased in very abstract terms. Another is they're highly malleable under redefinitions. Another is they're unobservable, right? They can indirectly be related to stuff, but you can't ever actually see them. They don't exist in physical space. They're not back reacted upon by the stuff that exists. There's just a long list of things that are characteristic features of hidden, with these so-called latent variables you introduce to make it. And these are exactly the features the wave functions have. Like, it's hitting all of them, they get hit on the nose. So when you look at this, remember I mentioned there are all these different directions that lead to non-Markov vanity. This is another one of the directions, is looking at the wave function and going, what metaphysical category does this fit into? Is the wave function straightforward ontological furniture? It's not quite, maybe, I don't know. I know Tim Maudlin, right? He has a view the wave function is a distinct kind of ontology. There are many views, right? Maybe the wave function should be understood as purely epistemic. That's got all kinds of problems. There's the view that maybe the wave function is a monistic ontology. It is the only thing that exists in the universe. This is a whole list of views. None of them quite exactly fit. But this other category, that the wave function is a latent variable, ironically enough, sometimes called a hidden variable, that you introduce to get a Markov-looking description, giving you what's called a hidden Markov model, it just nails what the wave function looks like so perfectly. Now, of course, if that's your view of what the wave function is, then your immediate reaction is, well, then what we really have is a non-Markovian process, and the wave function was merely introduced to give us a law-like description. And so what I would say to this, David, is I would say, if the view is that the actual metaphysical pictures, we've got some non-Markovian stochastic process, and it doesn't have all the ingredients you want, there's stuff that's unfixed, but I can do a mathematical transformation. Take all that stuff that isn't fixed and turn it into something like a latent variable, a wave function, that we can't observe and whatever. And now we can turn it into a Markov process, we can write a law down. I would say, if that's what you want to do, go for it. In the non-relativistic case, with fixed numbers of finite many particles, works great. And I should say that Bohm isn't even the only game in town there. There's another theory. So I just reread, so people, may not know, but David just taught David and Barry Lower, they taught a course this past academic term at Rutgers on statistical mechanics and time and chance, David's, amazing book on the difference, the past, the future, and all this stuff. So I had an opportunity to reread the book, and also I sat in on the course, and David will know that I was sitting on the course. The book talks about how all of the major interpretations, they all have a similar kind of deterministic, structure, a bilateral deterministic, Everett and Bohm and so forth. And this makes it very hard to get statistical mechanics to underwrite thermodynamics. You have to work really hard. And much of the book is devoted to the project of how hard is it? How can we do it? And then at the end of the book, last chapter, David's like, well, but maybe we should just take seriously that quantum mechanics should be replaced by a genuinely chancy theory. And the theory that David considers is the GRW theory, which was concocted in the 1970s. G is for Girardi, R is for Mini, and W is for Weber. And this theory has genuine chances in it, and the genuine chances make a lot of problems simpler to deal with, right? And so if that theory works, it would really make the intertheoretic reduction of thermodynamics, statistical mechanics much easier, and many of the problems would be simpler. But I should mention that there has been a stochastic theory, not GRW, for a very long time. All the way back, at least as far back as the 40s. In fact, if you read Hugh Everett's unpublished 1956 dissertation all the way to the end, to the final section discussion, by the way, I think it's fantastic. Everyone should download it and read it. It's a brilliant piece of writing and a lot of brilliant philosophy. Even if you're not a many-worlder, there's so much really good stuff in there. But at the very end, he considers all the alternatives that he was aware of at the time. Bohmian mechanics, he was certainly aware. Bohm's papers and book were the first 3 citations in Everett's thesis. He clearly read them all deeply, took to heart all the lessons about decoherence, all that stuff. So he talks about Bohm's theory. He also talks about a theory that he calls the stochastic process interpretation. That's what he calls it. And the stochastic process interpretation doesn't have a wave function in it. It's an attempt to just take the degrees of freedom and give them stochastic laws that will carry them to the right outcomes with the right Born rule probabilities without a need for a wave function. And the person he mentions as having worked on this is somebody named Fritz Bopp. There is another Fritz Bopp alive today who's not the same person. He's not just like an infinitely long-lived individual. There was a different Fritz Bopp. He worked on this. Imre Fenjes started working on this in the 40s and the 50s. He's more prominent, more well-known. But the most famous person associated with this, and David, you probably maybe know, is Edward Nelson, 60s through the 80s. So 1966, Edward Nelson published a paper in which he claimed to be able to get quantum mechanics with no wave function, to get quantum mechanics out of a stochastic process. And he worked on this from the 60s through the 80s. This became known as Nelsonian stochastic mechanics. It's an attempt to get quantum mechanics to emerge from a particular kind of Markov process called Brownian motion. And this theory, I would argue, is certainly no worse than Bohm's theory. It replaces Bohm's neat trajectories with stochastic trajectories, Markov-type Brownian trajectories. It's a theory with genuine chance in it, and the chance is happening at every moment, like in GRW. So this is a theory, I think, that would also do what you want GRW to do in the sense of making it easier to get quantum mechanics out.
Just one narrow point and one larger point. Jacob, what you've been saying might leave the impression, I don't know if this is the impression that you mean to leave, but might leave the impression that any kind of stochastic process at the fundamental level is going to be able to do the job for statistical mechanics that GRW does. That's not true.
Correct. Yes. Right.
Think about, say, something like Penrose's collapse theory, which is also stochastic. That demonstrably will not do the job.
Yeah.
So merely having a stochastic process, and in particular, I don't see any reason to be confident that having the kinds of stochastic processes that come up in your theory, but I'd need to hear a lot more about this, are going to be able to do a job like the GRW stochasticity does for statistical mechanics. Anyway, just being stochastic is surely not a sufficient condition for that.
Agreed.
Good.
Yeah. There's much more to say about that. Yeah.
The larger point, and I guess this is the last thing I'll have to say, and I'm just repeating something that I've said often in the course of this discussion, is, look, I began my comments by saying something about the kind of theory that I think would be a useful contribution to this kind of discussion. And what I meant was a realistic theory in the sense that I was talking about. If one isn't going to demand that, one might as well go with the Copenhagen interpretation or something like that. It gives perfectly good predictions about how experiments are going to come out. So what I was trying to evoke in my initial remarks, in my initial disclaimer before my real remarks began, was a mood like this. Look, I see in some of Jacob's remarks the outlines of what I would call an unambiguously realist theory, in the sense in which I've always understood realism. And I wrote down the kind of unambiguously realistic theory that I was able to extract from some of Jacob's comments. And commented on some of its features, commented on some of the features that make it look promising and other features that makes one worry about it. Okay. And that was the structure of my remarks. When Jacob started talking, the first thing I wanted to know was whether he was interested in the way that I was in saying, look, if this is going to be an interesting conversation at all, it's going to be a conversation about classically realistic theories. And a lot of the remainder of the discussion was, at least from my point of view, a struggle to see whether what Jacob had in mind was really realistic in this sense or not. And I wish I could say that I came out of the discussion with a clear answer to that question, but I don't feel like I'm coming out of the discussion with a clear answer to that question. As I've said, I see ways of extracting something that I have no hesitation in calling exactly the kind of realistic theory that I'm interested in from some remarks of Jacob. Jacob may regard this as a distortion of his remarks, but I'm able to extract this theory. This is a theory which I find interesting, but also worrisome, and that's the impression that I tried to give. And then most of the rest of the conversation, as I saw it, was an attempt to get to the bottom of whether whatever it was that Jacob actually had in mind, of which my remarks were apparently a distortion, whether what he had in mind satisfied my conception of what it is to be the kind of solution to the problems at the foundations of quantum mechanics that was going to interest me at the end of the day, which was a genuinely realistic solution. And I can't say, and maybe this is just my fault or my lack of imagination, that I came out of the conversation with a clear yes or no answer to that question that I understand. So that's where I'd be inclined to leave things.
Okay, let me summarize a little bit. And I want to again express my appreciation both to David and to Robinson for this discussion. I hope we
As
can
do I, to both of you.
very, very interesting. So let me just start by saying there are other problems with the Copenhagen interpretation, right? I mean, I think Everett spells this out rather beautifully. The Copenhagen interpretation has two different forms of time evolution. And what Everett says is, whatever your view about whether you prefer one kind of time evolution, unitary evolution, or the other, linear evolution, or the other kind, collapsed probabilistic evolution, you can take whatever side you want. The stochastic interpretation that Everett's referring to takes the probabilistic evolution. Everett himself, Bohm, they take the linear evolution, whatever. Pick one side, it's something else altogether. To have a theory in which you've got these two different forms of time evolution and and just like ambiguity over when which one applies. This is just a measurement problem, right? And what Everett also points out about Copenhagen is, by assumption, because it takes for granted the classical description of the macroscopic world, that's an input into the theory. Everett points out this theory is, by its nature, incapable of accounting for the emergence of classical reality. It presupposes it, so it can't possibly derive it. And to be clear, those are both out the door with my approach. My approach assigns an ontology to everything. There's only one kind of modal structure, these joint probabilities that define the stochastic process. In some situations, we get the emergence of initial value formulations with nice dynamical rules separated from initial conditions. These just emerge from the theory. That's a picture, and the picture applies up and down. Small systems, big systems. There's only one. There's not two different kinds of laws available. There's not. It's not like you've got probabilistic laws on the one hand. There's no special status assigned to measures. The measurement problem, not uniquely in my approach, obviously all the different interpretations, they all resolve the measurement problem one way or the other, provides one way to resolve the measurement problem. And it doesn't run into the contradictions we run into with the other theories. So I would say that's progress. Now, would I claim that this is definitely the final theory? Well, absolutely not. For one thing, our universe has gravity in it, and we keep talking about applying a theory to the whole universe. I hasten to point out that the observable universe is, first of all, an open system. We don't know what's beyond it. But secondly, at the scale of the observable universe, cosmological gravitational effects are not negligible. And certainly if there's anything bigger than our observable universe, which we have every reason to think, quantum gravity is going to be really important there. And I'm not claiming to have a theory of quantum gravity. So this is intended to be a much more modest theory at this point that applies to meso and macroscopic systems ignoring the effects of gravity. And again, I still think that's a form of progress because I don't think the other theories get us there. So I just want to say that as background, why we would think this is an improvement over something like the Copenhagen interpretation, which I think needs to be said as a defense. Now, there were two other very quick things I want to mention before we close. One of them was this question about eigenfunctions, and I think this needs to be said. So in David's remarks, he said there's no such thing as an eigenfunction of configuration, eigenfunction of position. That is actually not correct. So what's true is that in the Schrödinger representation, this is now going to get, it's a technical question. Does a certain function exist? In the Schrödinger representation of the so-called Weyl algebra, you're right. There are no eigenfunctions for position. That's true. But this is not the only representation of the Weyl algebra. There's a beautiful paper by Hans Halvorsen, whose name I cannot immediately remember. I think it was from 2001. So it's, yes, right. So this is the paper 2004, Complementary Representations in Quantum Mechanics. It was in Studies in History and Philosophy of Modern Physics, in which he points out there are other representations. And in fact, there are representations in which there is absolutely a position eigenfunction. Although in such representations, there are not momentum eigenfunctions. But not a problem for me. I don't take momentum to be fundamental anyway. So that's fine. And in fact, the way you deal with David's question, how do we deal with an initial condition phrased the level of an exact position, is you use a different representation. It's an irregular representation, but I mean, that's just a technical thing that doesn't really matter. It's faithful. So you just use that representation, and then you can avail yourself of all these beautiful theorems in algebraic.
Yeah, that's great. And of course, that's not, as I emphasized when we were going along, that's not one of the
Wasn't a
things.
deal breaker. I do feel like it was worth mentioning.
Yeah, sure.
Then the last point is this question about locality. So I want to just say, I'm going to reiterate what David said. My claim is, to be clear, let me not say too many double negatives. I'm not saying that quantum mechanics is in fact local. If anyone has gotten that impression, that is not what I'm saying. There are varying ways to talk about locality. We can talk about whether correlations are local or non-local, and non-local correlations are perfectly fine classically. We can talk about whether a theory is counterfactually local in the sense that, is there some weird non-locality between counterfactual propositions? And arguably, EPR settled that. The quantum mechanics has clear examples of counterfactual non-locality that were then precisified by Bell. Then there's a stronger level. Is there causal non-locality? Is there a well-defined sense in which causes and their effects are linked across like distances over sufficiently short periods of time that this would require some kind of super luminal, faster than light causal influences? That's a different notion of locality. And then finally, there's signal locality. Can a human, an observer, an agent, send messages faster than light? And we're all in agreement that at least, unless something weird and exotic is happening with closed time-like curves and general relativity, that's not going to happen. So there's general agreement that non-local correlation is fine and is fine in classical physics. There's agreement that signal locality holds in quantum mechanics. Observers can't send messages to each other faster than light. Those are both in agreement. And the question is, what happens to counterfactual non-locality and causal non-locality? I am openly admitting that quantum mechanics exhibits counterfactual non-locality. The question is, does that mean it's causally non-local? That's that question. That's why I was very explicit in the papers. And David was nice enough in his remarks to make this clear. I'm talking about causal locality. And to talk about causal locality, we need to say something about what we mean by causal relations. My theory comes with, very naturally, an account of causation built out of the nomological, these conditional probabilities that link things together. And this is all spelled out in other work, including a paper that today was just accepted in Physical Review A. It's with so-called CHization equality that'll be out soon. But the theory comes with its own very natural notion of causation that's rooted in various parts of the literature. I can point people to references. There's some really good stuff. On that definition of causation, on that definition, you can impose locality. You can say that notion of causation is not allowed to go outside the light cones. And when you do that, what you find is you can violate Bell's inequality. You can violate it. And you can violate it only up until a very famous bound called the Tsirelson bound. Now, this is really interesting. People know that the Bell inequality is violated by quantum mechanics. We know that. Not a lot of people know that it can't violate the Bell inequality arbitrarily much. There's a tight bound on how much violation you can get. In particular, this bound is called the Tsirelson bound. It was proved in 1980, and you need the whole apparatus of quantum mechanics, traditionally speaking, the whole apparatus of quantum mechanics to derive it. It says that you can violate Bell's limitation by about 41%. You can go up to 141%. You can violate it by not quite 50%, and it's the 41% is because it comes from root 2. Root 2 is 1.414. So you can only violate it by so much, and one might naturally ask, is there some principle why we can only violate it so much? It was later work, Sandu Popescu and Daniel Rohrlich in the 90s, they tried to find some intuitive reason. Maybe if you violate it any more, then humans can send signals, but they proved that wasn't true. You can violate it by way more and still not let humans send signals. So there was this question left over. Why can quantum mechanics only violate the Bell inequality by so little, when it could violate it by way more without causing any conceptual or logical paradoxes? And this paper that we just accepted uses the notion of causation that we've introduced that comes directly out of this theory. If you were to ask, what good is this notion of causation? Here it is. This notion of causation, when you impose locality on that, gives you a theory that lets you violate the Bell inequality only exactly up to the Tsirelson bound. And that's really very elegant. And as far as I know, maybe there's something in literature I haven't seen, but you give me a theory of causation, you tell me what it means to be local, how high can I go? Tsirelson bound. And that's a really nice result that says that this notion of causation is actually doing something for us. And that's one reason why, again, I think that we're on the right track with this project. So I think that's worth mentioning. And I wanted to clarify my remarks because David's right. I don't want anyone to get the wrong impression that I'm saying that quantum mechanics is just local, full stop. That isn't what I was saying. I want to be very precise about exactly what I'm trying to say.
Well, after 2 hours and 40 minutes, which I found extremely useful, thank you to both so much. Even though we didn't really move too far past the questions of scientific realism and the formulation of Jacob's theory, I found all of that very, very engaging. I'm sure our listeners will too. So maybe we'll come back to this sometime down the road. But until then, thanks both of you for having this discussion.
So
Thank
lovely.
you, Robinson. Thank you, Jacob.